This is part 3 of a 3-part video. The final method which could be used to predict the drag of a rough surface is by conducting minimal span channel simulations. Here is a downsampled sketch of the computational grid of the full span channel at Arita 180. The size of the computational domain scales with delta, and the number of computational cells scales with Arita to the third. This makes the computational requirements for high Reynolds numbers flow extremely expensive. On the other hand, the computational domain of the minimal span channel scales with the viscous length. It only has to be large enough to capture the near wall streaks, which have a streamwise length of approximately 1000 viscous units and are about 100 viscous units wide. With increasing Reynolds number, the mesh density increases. While the physical size of the computational domain of the full span channel remains the same, the physical size of the computational domain of the minimal span channel reduces as the viscous scales become smaller with increasing Reynolds number. At Arita 540, the number of computational grids for the minimal span channel is only 0.52% of the full span channel. That's almost 3 orders of magnitude lower. This makes the minimal span channel simulations extremely cheap to run. Now, to simulate a rough wall minimal span channel, there are a few requirements which have to be satisfied, and they are documented in Chung et al. 2015. The first condition, which I have mentioned before, is that the span-wise length of the domain has to be at least 100 viscous units wide to capture the near wall streaks. Also, as we have explicitly gridded the roughness elements, the span-wise length of the domain has to capture at least one repeating roughness wavelength. And finally, the span-wise length of the domain has to be larger than k divided by 0.4 to ensure that the roughness elements are completely submerged in healthy turbulence. Now I would like to show you a quick validation of the mean velocity profiles of the minimal span channel. Here, I have the mean velocity profile of the smooth and rough case where h plus equals to 20 simulated at Arita 360 in a pipe. In the inset plot here, I have the velocity difference between the smooth and rough profiles. About 20 viscous units above the crest of the roughness elements, you can see that the profile remains relatively flat, which means that the downward shift in the mean velocity profile of the rough wall is constant in the outer region of the flow. This gives us a reliable estimate of the roughness function. Plotting the mean velocity profile of the full span channel, we observe that they are very similar to the pipe simulations, except in the outer region of the flow where the wake of the pipe is slightly larger. Here are the mean velocity profiles of the minimal span channel. You can see that the mean velocity profiles of the full and minimal span channel and pipe are identical up to a certain wall normal height. Above this wall normal height, the mean velocity profiles of the minimal span channel increases at an increasing rate. Looking at the plot of the velocity difference, it is found that all 3 flows collapses on top of each other. This gives us confidence that the minimal span channel simulations are able to provide reliable estimates of the roughness function. To test the accuracy of the minimal span channel in predicting the roughness function, we have repeated case S1, where we increase the height of the roughness elements while maintaining a fixed roughness height to wavelength ratio. Here, we maintain a constant blockage ratio and increase the height of the roughness elements by increasing the Reynolds number of the flow. Here we have h plus equals to 10 simulated at Arita 180, h plus equals to 20 simulated at Arita 360, and finally, when Arita is equal to 1080, h plus is equals to 60. This is the roughness function plotted against the equivalent Zangri roughness height, and you can see that the roughness function of the minimal span channel lies very closely to the roughness function of the pipe simulations. To conclude, we have shown that minimal span channel simulations are able to accurately predict the drag of a rough surface at a fraction of the computational cost required to simulate a full span channel. The work which I have presented here is published in the following paper. And here's the summary of the results which we have obtained in this 3-part video. Thank you.